In this video, we can discuss about work done in rotating a dipole in an electric field. Let us consider a region of uniform electric field represented by this arrow or this electric field line, and in which a dipole is placed. Minus q charge and plus q charge is separated by a small vector distance that is called a dipole. A dipole is placed at an angle theta 1. So we already studied when a dipole is placed in an electric field, it experiences a torque given by the equation tau is equal to Pe sine theta. Now the torque direction is like this. The torque acting on the dipole is trying to align the dipole in the direction of electric field. That is natural process. Now let us turn the dipole through an angle theta 2 opposite to the direction of the torque. That is not possible unless an external work is given. So by giving an external work, I am turning the dipole from an angle theta 1 to an angle theta 2 as shown in the figure. In between, let d theta is a very small amount of angle turned, then the small amount of work done to turn the dipole through an angle d theta is given by dw is equal to tau into d theta. This equation is similar to work done is equal to force into distance. The torque is the rotational analog of force, as well as d theta is the rotational analog of linear displacement. Therefore, this equation is the rotational analog of translational equation work done is equal to force into linear displacement. Here it is work done is equal to torque into angular displacement. So this equation gives small amount of work done by the external agent in order to turn the dipole through a small angle d theta. Our aim is to turn the dipole through an angle from theta 1 to theta 2. Let us substitute tau here, then dw can be written as Pe into sine theta d theta. Now what is the total work done to turn the dipole from an angle theta 1 to theta 2? So we have to integrate this equation. W is equal to integral of theta 1 to theta 2 dw is equal to integral of theta 1 to theta 2 Pe sine theta d theta. Now Pe can be taken out. Pe is taken out, then what remains is integral theta 1 to theta 2 sine theta d theta. Now integral of sine theta d theta is nothing but minus cos theta. Therefore Pe into minus cos theta, lower limit theta 1, upper limit theta 2. Substituting lower limit and upper limit, I will be getting Pe into minus of cos theta 2 minus of the minus plus cos theta 1. W is equal to Pe into cos of theta 1. Theta 1, since it is positive, can be written first, minus cos of theta 2. This equation gives work done by the external agent to turn the dipole from an angle theta 1 to an angle theta 2. Now let us consider a special case in which theta 1 is equal to 0 and theta 2 is equal to theta. Theta 1 is equal to 0 means there is no angle between electric field vector and electric dipole moment. You know, electric dipole moment is always acting from negative charge to positive charge. This is the electric dipole moment vector, and that electric dipole moment vector is parallel to electric field, means the dipole is placed in the direction of electric field with the positive charge on the top and negative charge here on the bottom. So that is why electric dipole moment and electric field in the same direction. Then theta 1 is equal to 0, theta 2 is equal to theta. Then this equation becomes W is equal to Pe into cos of 0 minus cos of theta. So that means W is equal to Pe into 1 minus cos theta. So this is a special case of that work done. Now let us assume what is potential energy. The potential energy, when we study the potential energy, actually the potential energy should be studied with respect to a reference point. We assume that when the dipole is placed perpendicular to the electric field, potential energy is 0. Potential energy is not minimum when the dipole is placed perpendicular to the electric field. Potential energy is assumed to be 0 there. So that is taken as the reference point to study potential energy. So theta 1 is equal to 90 degree, and from there the dipole is oriented or aligned at any other direction theta 2 is equal to theta. Then what is the work done? The work done is given by, according to this equation, PE into the reference level cos of 90 minus any other direction cos of theta. So cos of 90 is equal to 0, therefore W is equal to minus PE cos theta. So this equation is considered as the potential energy of the dipole in an electric field at any orientation. Therefore U is equal to minus PE cos of theta in terms of vector U is equal to minus of P dot E. Now let us consider different cases of potential energy. So you can see the first case when dipole is placed parallel to electric field. Dipole is placed parallel to electric field means this is the direction of electric field. This is the dipole minus q charge plus q charge. Dipole is placed like this so that dipole moment vector is parallel to electric field. Dipole moment vector is always from negative charge to positive charge. So in this particular case theta is equal to 0. So we already studied U is equal to minus PE cos of theta. That is the equation for potential energy. Now right now what is the potential energy of the system? Potential energy of the system is equal to minus PE into cos of 0. Cos of 0 is equal to 1, therefore U is equal to minus PE. Minus PE. That means the potential energy is minimum when the dipole is placed parallel to the electric field, where dipole moment vector and electric field vector are parallel to each other. What is the implication of minimum potential energy? We already understood that potential energy is minimum means the stability is maximum. So in this configuration, the dipole is most stable. That is why this particular configuration is called stable equilibrium. We already studied this particular concept. When dipole is placed in the direction of electric field with dipole moment vector and electric field are in the same direction, theta is equal to 0, and that configuration is called stable equilibrium. Why it is called stable equilibrium? Listen very carefully. So I am going to just displace this dipole by a small angle like this. So this is the electric field, this is the dipole minus q charge plus q charge. I'm just to displace the dipole by a small angle. At that time, you know what is the force acting on the charges. This is the force acting on the charges QE and QE. The positive charge experiences a force in the direction of electric field. Negative charge experiences a force opposite to the direction of electric field. These two forces create a couple, and that couple will bring the dipole back to the original configuration. So automatically, as soon as there is a displacement of the dipole from the stable equilibrium, the forces arises that will bring the dipole back to the stable equilibrium, and that is why theta is equal to 0 configuration is called a stable equilibrium. Now case 2, the dipole moment vector and electric field are opposite to each other. So that is possible only if the dipole is placed like this. Negative charge is here and positive charge is here. The dipole moment vector is always from negative charge to positive charge. Electric field is like this. So electric field and dipole moment vector has an angle 180 degree. So angle between electric field and dipole moment vector is 180 degree here. So potential energy U is equal to minus PE into cos of 180. Cos of 180 is equal to minus 1. Potential energy U is equal to minus P into minus 1. U is equal to PE maximum. So very carefully understand that at this particular position, the dipole is in equilibrium. Why the dipole is in equilibrium at this particular position? You can see the electric field and minus q charge and plus q charge here. So the force acting on minus q charge is always in the direction opposite to electric field like this, QE, and force acting on plus q charge is always in the direction QE. So that means these two forces are equal and opposite, therefore dipole is in equilibrium. But slightest displacement from this particular orientation, very carefully listen, slightest displacement from this particular orientation. Now this is minus q charge and this is plus q charge. The force in this charge will be like this, QE, and force in this charge plus charge will be like this, QE. Now look at the direction of the force. The direction of the force will not bring the dipole back to original configuration. Instead of that, the forces created will bring the dipole back to theta is equal to 0 configuration. It will rotate the dipole like this. So from this orientation, it will never go back like this. Instead of that, it will rotate the dipole like this and bring back to stable equilibrium configuration. So that means when theta is equal to 180 degree, at that particular position the dipole is in equilibrium, but it is unstable. Why it is unstable? Slightest change in the orientation will cause a torque or will create a couple, and that couple will bring the dipole back to stable equilibrium. That is why it is called unstable equilibrium. So theta is equal to 0 configuration is called stable equilibrium, where potential energy is minimum. Theta is equal to 180 configuration is called unstable equilibrium, where potential energy is maximum. Now theta is equal to 90, the dipole is placed perpendicular to the electric field. Theta is equal to 90, u is equal to minus p cos of 90, u is equal to 0. U is equal to 0 is not minimum, u is equal to minus p is minimum. Since the potential energy is intermediate here, the dipole will try to align in the direction of electric field by rotating itself. So at any configuration, at any angle theta, the potential energy is there in the dipole which is placed inside the electric field. Every system will try to attain minimum potential energy. Under this potential energy, the dipole will turn itself and try to align theta is equal to 0 configuration.